So, today we are going to have our last formal class on conductive heat transfer, and we are going to end the study of conduction with a topic which is very common in everyday applications. We are going to talk about extended surfaces. So, what is an extended surface? An extended surface generally refers to a solid where inside the solid the conductive heat transfer takes place, and from the surface, exposed surface of the solid, we are going to have convective heat transfer. So, through the solid we have conduction, and from the surfaces of the solid exposed to a fluid environment we have convective heat transfer. Now, one of the major examples of extended surface heat transfer is the case of fins. Now, you probably have heard about this term before. What a fin generally refers to, which is a thin solid surface through which is used for enhanced heat transfer. You would see those fins in various applications. Previously, when you could look at the back of the refrigerator, you would see those extended surfaces. If you look at the radiator of a car, or the radiator of or the engine block of a motorbike, you would see that there are protrusions of solid which looks like thin plates, and those thin plates provide the additional area available for convection. So, generally the heat transfer coefficient from solid to air is quite low. So, we cannot change H without expending more energy, that means making the fluid flow over the solid at a faster velocity. What we can do is we can enhance the area, increase the available area which is to be utilized for convective heat transfer. So, Q equals H A delta T. This A, the area available for convection, if it can be increased by putting certain fitments to the hot surface which are to be used for additional heat transfer, and they are collectively called as fins. Fins come in different shapes, sizes, and in any case you have to justify the use of fins, because if you have seen the radiator of a car, there is significant amount of fabrication cost involved in making the fin, and also there is going to be some cost related to attachment of the fin to the hot surface. So, unless those fins meet certain fundamental criteria of additional or enhanced heat transfer, the use of a fin is never going to be prescribed. So, one must know what are the benefits that one is going to get out of having the fin on the hot surface, what is its efficiency, what is its performance, and based on these two parameters, not only you decide whether to attach a fin, you also decide what kind of a shape, what are the design parameters of an ideal fin should be. So, we will in this class we will have a quick look of the fins, the governing equations, solution of the governing equation for some specific boundary conditions, which would give rise to an idea of what is the performance index of a fin and what is the efficiency of a fin. So, let us start with the very fundamental case of when a solid surface is experiencing convective heat transfer, and we would like to see the different shapes of fins which are commonly used in everyday applications. So, let us first take a look at what a fin would look like, what an extended surface would look like. So, this is a solid whose temperature is, let us say, at Ts, and we have some air or some fluid which is flowing over it. So, this is at Ts the temperature, and the area exposed for convective heat transfer is A. So, the heat loss from the surface is simply going to be Q is equal to H times A Ts minus T infinity. So, as I said, this H is more or less fixed. The moment you fix T infinity, the moment you fix what is the velocity of the air which is moving, what is the shape and size of the solid, and so on. So, I do not have any control on H, but I can enhance this area to increase the amount of heat transfer by the application of extended surface. So, these extended surfaces are commonly known as fins. So, you can have the fins generally look something like this, the shape of the fin with which we are mostly familiar with. So, this is what the fins look like. Example of extended surface area. So, this is two fins which are connected to a base, and you have flow of, let us say, air at T infinity with some velocity, which is going to give rise to a convective heat transfer coefficient of H, and the temperature of the fin, let us denote this as Ts, and if this is my x direction, then my Ts is going to be a function of x, how far you are from the base, and let us say the temperature of the base is Tb. So, the problem that we deal with is to how to extract more heat from the surface using convective heat transfer, and also having these attachments, the fins on top of the surface, which enhances the area available for convection. But making these fins, fabricating these fins, attaching it to the base obviously would involve some cost, and we would look at what is the ideal situation, what is the basic requirement that you need to fulfill in order to prescribe the use of the fin. So, there are several types of fins which are commonly, you would see commonly. So, this is example of a straight fin, the one that I have drawn over here. So, this is an example of a fin. And its width is, let us say, W. It has a thickness equal to T, and this is the x direction. So, this is a straight fin of uniform cross section. So, here you can see the cross sectional area of the fin is equal to W times T, which remains fixed, and the temperature of the base is Tb, whereas the temperature of the fin is, let us call it as Ts, and this area is available for convection. The area at the top and the area at the bottom, they are available for convection, whereas you are going to have conductive heat transfer through the fin. So, as the heat comes towards the tip of the fin, part of it is going to go out, going to leave the surface by convection, and so there would be diminishing amount of conductive heat which is moving towards the tip of the fin. So, it is the example of a straight fin with uniform cross section. On the other hand, you sometimes you also have fins which look like this. where the cross sectional area does not remain constant and you have a fin whose cross sectional area is going to be different So, if you look at this, what you would see is the cross sectional area of the fin keeps on decreasing and the convection area, the area available for convection, that is more or less fixed, but the area available for convection conduction keeps on decreasing. So, it is an example of a straight fin of non-uniform cross section. This is another example of fin. Some of the fins which are commonly seen in applications So, these are known as annular fins. So, these annular fins are connected to, so this is the cylinder which is hot, whose temperature you would like to reduce. So, you attach an annular fin and this is the surface which is additional surface which is available for convective heat transfer. So, what we see that the purpose of the fin is to provide additional surface area for convective heat transfer. The fins can be of different shape, different size, its cross section which the area which is to be used for conduction may or may not remain constant. So, these kind of variations in fin size and shape are possible. So, now what we are going to do is we are going to find out, we are going to derive a general formulation for the heat transfer, simultaneous conduction and convection from the surface of a fin, and using that governing equation with appropriate boundary conditions, we would like to obtain what is the temperature profile inside the fin. Because if we can find out what is the temperature profile of the fin, then if I consider x at x equals 0 to be the base where the fin is attached to the base. So, x equal to 0 refers to the point where the fin is attached to the base from where you would like to extract the heat, then minus k a suffix b, where ab is the area of the base at which the fin is attached, times dt dx at x equal to 0 would give you the amount of heat that the fin extracts from the base. So, if you look at this figure once again, if this area of the fin over here, let us say this is the area is AB. So, the amount of heat which is taken up by the fin at steady state must be equal to K times area at the base times dt dx at x equals 0, where x starts from here. So, minus k AB, which is the area of the fin at the base, times dt dx at x equal to 0 gives you the amount of heat taken up by each of these fins. Okay. So, this would give you an idea, if you are making any additional benefit by having the fin. So, if you do not have the fin, then this area at the base would still be available for convective heat transfer. So, in that case, the whole of AB would be exposed to whatever is flowing here with H and T infinity. So, if I did not have the fin attached to this point, the amount of heat transfer in absence of fin, the amount of heat transfer would simply be equals H times A B times T of the surface minus T infinity. Okay. So, this is the amount of heat which would have been taken up by the flowing air if the fin is not there. The moment I attach a fin, the amount of heat transfer must be equal to the conductive heat transfer at the base. So, it is minus K A B dt dx. So, if you look at these two quantities, this is when the fin is not present and this is when the fin is present. So, the performance, the effectiveness, all these definitions should have these two quantities either in the numerator or in the denominator. Okay. So, what would be the effectiveness of a fin? If it is there, how much of heat it is extracting as compared to if it is not there. So, these two quantities over here would give you some idea about what is the performance of the fin. So, the efficiency of a fin, which is, let us call it as eta times F, is defined as the actual heat transferred divided by heat which would be transferred if the entire fin area the actual heat transferred with fin, heat which would be transferred if the, I would make it easier, actual heat which would be transferred without the fin. I'll since I have cut it so many times, I'll write it once again, just to make sure that the concept is clear to all of us. There are two concepts which are to be defined here. So, when I talk about effectiveness and efficiency, what exactly do I mean? In the case of effectiveness, I have to decide whether having the fin makes any sense. Should I have the fin or shouldn't I have the fin? When I look at the fin efficiency, I am trying to find out how efficient is the fin. So, let us first talk about efficiency. When I have decided that yes, I am going to use fin for a specific geometry, for a specific operation or for a specific application, now I am going to think, when do you think the fin is going to be maximum effective? Now, the fin is the gradient which is responsible for heat transfer from the fin to the atmosphere is simply temperature of the surface of the fin at any location, which we denote as Ts, and temperature of the fluid, which is a constant which we denote as T infinity. So, the amount of heat transfer from the fin is dependent on Ts minus T infinity. This temperature of the fin Ts is a function of x. It's equal to Tb, that means temperature of the base, and as I move, if this is a fin and this is my base, this is at Tb, and as I move towards the tip of the fin, the temperature gradually decreases. Okay. Since the temperature gradually decreases, so you start at 100 degree and the air is blowing at 25. So, as you move towards the tip of the fin, the temperature gradient between the surface of the fin and the air will continuously decrease. Since it decreases, you are going to have lesser amount of heat transfer from the fin as you move in the direction of plus x. Now, how do you make the process maximum efficient? How do you increase? How do you achieve maximum efficiency in the heat transfer process? That would only be possible if by some means, or if by the nature of the material of the fin that you have used, the entire fin is at the temperature of the base. So, instead of temperature of the fin varying at points decreasing as you move away from the base, if the situation is such that the entire fin is at Tb, then the heat transfer would be Tb minus T infinity, which would be a constant, and you are going to get the maximum amount of heat transfer from a given fin. So, that is how the efficiency of the fin is defined, which is actual heat transferred divided by the heat that would have been transferred if the entire fin is at its base temperature. So, like I am going to write the definition of the efficiency as actual heat transferred divided by heat which would be transferred if the entire fin was at base temperature. So, this would give you an idea of what is efficiency, because we always define efficiency in such a way that it has a maximum value equal to 1 or 100%. So, the actual heat transferred where the temperature is a decreasing function of x divided by the heat which would have been transferred if the entire fin was at Tb, the base temperature, that would be the logical choice to define the efficiency of a fin. So, now let us think about what is fin performance, okay? And this would tell us this would allow us to decide whether or not use of a fin is prescribed. So, the fin effectiveness or epsilon f is defined as fin heat transfer rate over heat transfer rate that would exist without the fin. So, if you do not have the fin, this entire area is at Tb, and of this much is the area where the fin was attached to. So, let us call it as area at the base. So, the fin heat transfer rate would simply be minus k times AB dt dx evaluated at x equals 0 where this is the point where your x where this is the direction of the decrease of x. Now, the heat transfer rate that would exist without the fin, it would simply be equals h times AB by T s at x equals 0, which is obviously equal to T b minus T infinity. So, this is the definition of the fin effectiveness, where the fin heat transfer rate is given obviously by the numerator, and the heat transfer rate that would exist without the fin is given by this, is simply h a b T b minus T infinity. Now, the rule of thumb is use of fin is rarely prescribed if epsilon f is less than 2. So, one can only prescribe the use of fin if its effectiveness is greater than or equal to 2. So, if this condition is met, then you go for attachment of a fin to the surface, and once you do that, then you look at what is going to be the efficiency of the fin. So, I will very quickly tell you what would be the form of the fin efficiency, the efficiency of the fin, and then we will see how that would give us an idea of what should be the shape of the fin. So, for a straight fin, uniform cross section, the eta f would be equal to the performance of the fin. This epsilon f would be equal to K p by h a c to the power half. Okay. So, this is the fin effectiveness. So, this is over here. So, what you see here, that epsilon f, the fin effectiveness is a function of thermal conductivity, is a function of P by A c, and it is also going to be a function of H. You would like to have the largest value of epsilon f possible. The larger is the value of epsilon f as compared to 2, the better is going to be its performance. So, what would be the nature of the fin material? If you look at the expression for epsilon f, once again, the material of construction of the fin should have a high value of thermal conductivity. That means K has to be large. The fin, the value of H should be small. The value of H small means the use of fins are only prescribed when we have heat transfer from a solid to a gas, which traditionally has low values of convective heat transfer coefficient. So, the fin material should be of large K, such that the entire fin is going to be at a temperature close to that of T b, not exactly at T b, but close to that of T b. So, the material of construction of the fin should be large. The fin is prescribed when you have heat transfer from the solid to the vapor, to the gas. So, that is why you would see use of fins mostly for the case of air, not for when a solid is in contact with a liquid which has a high value of heat transfer coefficient. So, and finally, P by A c should be large. That means, for the ratio of the perimeter to the cross sectional area should be large. That means, you are going to have a large number of thin fins attached to the solid surface from where you would like to extract the heat. So, it gives us idea about the material of construction of the fin, the shape of the fin, and the situation where fins are to be used. So, together they would give you a complete picture of when and why and how fins are to be used. I will very quickly go through the governing equation, the derivation of the governing equation, and then we can move on to the next part. So, the governing equation this is a conduction analysis where you have this being the fin which is attached to a surface. Okay, so, this is the fin. So, this is my x direction, and from here I have the conductive heat transfer, and let us say this is the surface from where I have convective heat transfer. So, if I enlarge this, it is going to look something like this. So, this distance is dx, this area available for convective heat transfer is DAS, which is going to lead to the convective flow of heat, and this area could be a function of x as well. This is the cross sectional area. So, you have q x by convection coming into the control volume, q x plus dx, which is the heat, convective heat going out of the control volume. So, by conservation I can write whatever heat is coming at this point must be equal to whatever heat that is going out through this surface and whatever heat is going to be lost by the convection process. So, this is just a conservation equation. The heat coming in must be equal to the heat going out by conduction and heat going out by convection. And we also understand that my q x is equal to minus k A c, AC being the cross sectional area dt dx, and q x plus dx can be written using Taylor series expansion as q x plus dq x by dx times dx. So, this is just the expansion of this. So, when you put these into the equation, what you would get is, and we also understand that dq convection must be equal to h dAs times T minus T infinity, where T infinity is the temperature of the fluid surrounding it. So, this is AS and this is AC, which we have to keep in mind. So, when I put this back in here, what I am going to get is, as my governing equation is as AC times dt dx minus h by k dAs by dx times T minus T infinity. So, this becomes the governing equation, and if I expand this, the final equation that I am going to get is this is the final form of the equation that I am going to get. So, this would be the governing equation for heat transfer utilizing a fin. Now, instead of this fin having a variable cross sectional area, if I assume that the fin is just like this, a fin with constant cross section, then this term would disappear, and what I am going to have is only the first term and the second term to be equal to 0. So, if I define T minus T infinity to be equal to theta, and if I assume that AC is not a function of x, then the same governing equation can be written as d2t dx square. AC is a constant, so this term would disappear, minus 1 by AC h by k times theta, and dAs dx is simply going to be the perimeter of the fin would be equal to 0. So, what I say is dAs by dx is P, which is where P is the perimeter of the fin, because AS is simply P times delta x, P is the perimeter times delta x. So, this would be the reduced governing equation. I will call this as theta as well. So, d2 theta by dx square minus 1 by AC h by k times p into theta to be equal to 0. So, for a fin of constant cross section, I will expand this equation a bit more, where you are going to get is that d2t dx square minus h p by k a c times theta to be equal to 0. And if I assume this to be equal to m square, then it is d2 theta by dx square minus m square theta would be equal to 0. So, this is going to be the governing equation for a fin of constant area. And the solution of this equation, solution of such kind of equation, these are homogeneous second order differential equation. So, your theta x would simply be equals C1 e to the power mx plus C2 e to the power minus mx, where m square is h p by k a c. So, that is a standard solution which you can obtain. So, you need two boundary conditions for this. One is theta at 0, at x equals 0 is the temperature is known, which is T b minus T infinity, and let us call it as theta b. So, the first boundary condition is that the temperature at the base is known to me, which is T b. So, T b minus T infinity, I call it as theta b. The second boundary condition can have different variations like A, B and C. So, what would I get in as the second boundary condition can vary. Let us say I have a fin which is very long. So, what is going to happen if the fin is very long in this direction, then the temperature of the tip most likely is going to be very close to that of the air. So, for a very long fin, the boundary condition could be that as x tends to infinity, temperature of the fin is equal to T infinity. That is one condition which one can use. Okay. If the fin is short, but its thermal conductivity is very high, then what is going to happen is the entire fin is going to be at a constant temperature which would be very close to that of the base. So, a short fin of very high thermal conductivity, the boundary condition at x equal to L, that means at the edge is going to be T is equal to T b. So, that is another possible boundary condition that can happen. The third type of boundary conditions that can happen is that whatever heat comes to the tip by conduction must be convected out through the cross sectional area which is exposed to the ambient environment. So, what is the amount of heat which comes to the tip? It must be minus k AC times dt dx at x equal to L. That is the amount of heat which comes to the tip by conduction through the fin. And if all of that at steady state, since it has to dissipate out of the cross sectional area by a convective process, the amount of heat loss by convection from the tip of the fin would be H times AC times T at the end, which is T L minus T infinity. So, these different types of boundary conditions are possible, and based on that the fin equation has been solved. You can look at the textbook for the various forms of the equations, various forms of the temperature variation, the temperature form, the form of the temperature for a fin of infinite length, of short length, but very high thermal conductivity, or for a fin whose tip is active. That means, the amount of heat coming to this to the fin end must be dissipated out. So, these combinations, the first condition is always fixed, that the temperature at the base is known, that is at x equal to 0 the boundary condition is known. What happens at x equal to L? we have 3 or 4 different types of boundary conditions, and for each of those boundary conditions, these solutions are available in your text. So, you should take a look at them, but you should also be very careful about the alternate conduction analysis and realize that the assumption of constant cross sectional area may not be valid in all cases. For example, in the tapered fin which I have drawn, the area is not a area available for conduction is not a constant. So, which could give rise to interesting problems. And the fin material should be of high thermal conductivity. The shape of the fin should be thin and closely spaced, and you are going to use fins only when you heat transfer when you have heat transfer between the solid and a gas, generally not between the solid and a liquid. And there are 2 parameters which define whether or not a fin is to be used or what is the efficiency of the fin. The fin can be used only when its performance is the index is greater than equal to 2, and it is going to be most effective when the entire fin is at its best temperature. So, that is all I wanted to cover in this class. I guess you have had some idea about what is involved in heat transfer from an extended surface. There are vast literature and information available in many textbooks and many handbooks about how to design fin, when to add fin, the fabrication techniques, the way you attach the fins to a surface, and so on. So, if you are interested, you can take a look at them, but always remember the fins are useful way the attachment of fins is a useful way to enhance heat transfer, and they simply provide an extended surface, and therefore, extended surface heat transfer is an important topic in conduction heat transfer.